Greetings, everybody. Let's continue our discussion of flux integrals. So in this video, let's do an example where we're asked to calculate the flux of a vector field f equal to x comma y across the curve c, where c is just going to be given by the curve y is equal to x squared in between -2 and 2. And we want to calculate the flux to the right of the direction of travel along C. So how do we go about doing this? Well, since we're given it as y, just a function of x, we kind of get this immediate parameterization at just x is going to be t, y is going to be f of t, so t squared. And t is going to be running in between -2 and 2. So if we take the dot product, or if we take the derivative of that thing, we just get 1 and 2t. Looking at the length of that vector, we get the square root of 1 plus 4t squared. So that our unit tangent vector just looks like r dot over the length of r dot, which just looks like 1 over the square root of 1 plus 4t squared, and 2t over the square root of 1 plus 4t squared. So now for our normal vector, we look at the derivative of the unit tangent. And so the derivative of the unit tangent is just going to give us a -4t over 1 plus 4t squared to the 3 halves, 2 over 1 plus 4t squared to the 3 halves. And so what we're going to want then is a unit normal in that direction. Well, the vector that we just calculated has this common factor of 2 over 1 plus 4t squared to the 3 halves inside it. And so when we have kind of that common factor, that scalar function that's there, we can pull that factor out. And then in normalizing, what happens when we normalize that thing is that the scalar factor is probably just going to cancel out. And so in normalizing it, we can just ignore that scalar factor that we pulled out and really just normalize the vector that was already there. Now generally this kind of just simplifies the computation algebraically for what we're actually doing. And so we can just normalize a -2t and 1 instead of normalizing this big algebraic expression where we've pulled out this, where we didn't pull out that algebraic factor. And so if we just normalize -2t comma 1 instead of the whole expression, then we get, oh, what a coincidence, we get our scalar vector back, so 4t squared plus 1. So the unit normal that we want then is either the -2t over the square root of 4t squared plus 1, or it's negative of that thing. And so now we kind of look at our curve and say, all right, which one of these normal vectors do we actually want? Well, if we want it to the right as we're tracing out that curve, then we're wanting our normal vectors in this direction. And so kind of our key to know with that is that whenever t is positive, it's in the positive x direction, and so that's going to tell us that we want a positive x value whenever t is going to be positive, and so we want our unit normal to be this vector. So we want it to be a 2t over the square root of 1 plus 4t squared and -1 over the square root of 1 plus 4t squared. So now that we've got our unit vector in that case, we look at the flux integral. So that's the integral over the curve of f dot n ds. We've got our unit normal. Our parameterization was t squared. Our length was going to be 1 plus 4t squared, square root of 1 plus 4t squared. And so ds being our ds dt looks like the norm of r dot dt, so that gives us our square root of 1 plus 4t squared dt. If we take all of those, evaluate our vector field along the curve, so x is t, y was t squared, so we get t squared for that. Plugging all of those into our flux integral just gives us the integral from -2 up to 2, t squared dotted with our unit normal, 2t over the square root of 1 plus 4t squared, negative 1 over the square root of 1 plus 4t squared. We have our square root of 1 plus 4t squared dt being our ds. So that square root cancels the square roots in our unit norm, our unit normal. So we've got the dot product of those two vectors to eventually give us 2t minus t squared, or 2t squared minus t squared. So we've got the integral from minus 2 to 2 of t squared, which just eventually gives us the value of 16/3. And so here's another example of computing a flux integral in 2 dimensions, kind of from start to finish. So I hope you've enjoyed this. I hope it's been insightful, and I'll see you in the next video when we're talking about circulation. See you then.